Okay, hope you all had a good spring break. Like Kevin announced yesterday, the homeworks are actually due next week, and the project milestones, though, are due today. I think you can submit it on BSpace, right? Okay, so, next Tuesday, we're going to have project mini updates, which is going to be about 5-minute presentations by every group. And we'll send out information about what we want to see in those presentations soon. Okay. Are there any other questions about projects or the class in general? No? All right. So we're going to start the third section of this course today, which is going to be on the third part of the book on analysis and verification mostly. And also we'll cover some advanced topics, topics which are sometimes not even in the book, so we'll assign reading for those. Today's topic is something fundamental to this area of analysis, and in fact to any system design, not just embedded systems, but systems in general, which is the notion of a specification. How do you write down a mathematical description of what your system must do? So today we'll talk about a particular way of writing specifications, which is temporal logic, and this has become quite widespread in the past 30 years or so since it was introduced. And then on Thursday, we'll talk about another way of writing specifications. So what is this notion of a specification? Well, the specification is something which tells you if your design is correct, right? So informally in English, you'd say that a design is correct when it meets a specification, whatever this is. The word requirements are also used in place of specification. But always correctness is modulo the environment, right? So you say the design is correct when it meets the specification in the operating environment. So in order to figure out if you've built the right system, you need two things. You need the specification, and you need a description of the environment, right? Back in February, when we talked about state machines and modal models, we talked about how you can model the environment of any system also as a state machine, right? And in fact, the notion of non-determinism is quite useful there. So we went through a couple of examples then. Today we'll talk about the idea of a specification. How do you write down a specification mathematically? Surprisingly, in the real world, the idea of just writing down a mathematical specification hasn't really caught on. What people do today is write English documents, pages and pages of English documents. And so temporal logic is one way to make those English documents precise. So I'm going to show you a few examples of these English language specifications from some real embedded systems. So there's this very nice saying that was appeared in a paper 30 years ago or so, which says that if you have a design and it doesn't have a specification, then it can't be right or wrong. It can only surprise you, right? It can only be surprising. And this is true. So if you don't write on a specification, then there's no way of figuring out whether you built the right thing or not. Okay? So the alternative, of course, to writing a specification is you say, oh, I'm going to run a bunch of tests. So the easiest thing is, let's say, when you do an introductory programming class, you write down a sorting algorithm, and then you say, okay, I'm going to give it a few example arrays. I have the original array and I have the sorted array. If I run these tests, I'm happy, right? And that may work for that assignment, but even sorting algorithms surprisingly are hard to get right. Sometimes you're off by one in the condition or something like that. So it's good to write mathematical specifications. Simply running a few tests, especially for embedded systems, is not enough. And in the context of this class, we've seen that embedded systems are deployed much more than other systems in safety critical applications. So there have been some, in the area of embedded systems and security, there have been some terrible failures, which in part have arisen from the problem of not writing down good specifications. So the first one up there on the top left is an example of a rocket failure in the Ariane program in France. In 1996, the Ariane rocket took off, and midway during the launch, it just exploded. Right? Does anyone know what happened? what was the cause for this failure? No? It was an overflow problem. It was a conversion problem from floating point to fixed point, I think, and it wasn't done right. And so the quantity that was interpreted at the end was wrong, and the rocket exploded because I don't know the details, but maybe it tried to go too fast or veer from its path or something like that. So this was really a software bug, a really mundane software bug, right? That all of us encounter when we first start programming. But it could have been avoided, right? Certainly, it could have been avoided. You might have heard also recently, or not so recently, but maybe 5 or 10 years ago in the news, there was this spacecraft sent to Mars, and it failed because there was a conversion problem, metric to the English system, right? I think so. This is another example of this units conversion problem, which we think is really this mundane thing, but it surprisingly turns up in these kinds of applications. So this could have been caught. This would certainly have been caught with the tools we have today for verification. These kinds of software failures are easy to catch, and in fact, the European Space Agency now has extensive verification tools running on their code to find floating point errors and overflows. This other one is another celebrated failure from Intel. It was more of a PR failure, that at least that's what many people say. Intel released the Pentium to much fanfare, and their engineers actually, I think the story goes, the engineers knew there was a bug in the floating point division algorithm, but they said, nobody's going to find out. It's this stuff that only these wonky scientists will work with, and the public at large is not going to figure this out. But it turned out that somebody found it, and it became just a snowballing thing that if you run this program, you will see that it produces the wrong answer, right? And that started spreading, and the internet was just coming up at that time. And so Intel had to do a big recall of all their chips because of this error in the floating point division algorithm. And then more recently, all of us are too painfully aware of the effects of viruses and worms, right? And that's also fundamentally a verification question. So in the context of embedded systems, there are 3 areas that today's lecture and this sequence of lectures are going to touch upon. The first is specification, which is how do you write down a mathematical statement of the design objective, what the design is supposed to do. The second is verification. We'll get to this in about 2 weeks. So once you write down the mathematical description of the design objective, then you need an algorithm. How do you construct programs that will check automatically if your design meets the specification? Okay, so that's the verification question. And the third question is even going beyond verification. So imagine if you could just write down the specification of your system, just a mathematical description of what it should do, and you had a compiler produce the correct program for you, right? That's what synthesis is. So a controller synthesis is you're given an incomplete design, and you want to synthesize the control strategy so that the specification is met. Okay, so you're already exposed to model-based design, especially in the area of embedded systems. You've already used a kind of specification, which is you can think of the LabVIEW models that you constructed as a form of specification. It's a rather detailed specification because you actually describe everything in the system, but you do it at a high level, right? You don't actually write the code, and the model-based design tools from NI produce the code for you. So in model-based design, you start with a model. Think of this as a LabVIEW program, for example, and a specification, which is what the program is supposed to do. A verifier is a box or a program which will take in these 2 inputs, and it will produce one of 2 answers, yes or no. So it's a decision procedure. It produces a yes-no output. And what the verifier is doing is checking this particular question, which is, does the model satisfy its specification? Okay. And if yes, then you're happy because at least the model satisfies the specification, and then you can go ahead and compile a program from the model. But if not, you typically get some feedback. You get an error trace, and the error trace, think of it as it's a sequence of events that shows you how something wrong can happen in your system. And you can use that to debug your system and revise the model or revise the specification, because sometimes the specification might not be correct as well. Okay, so so we're going to talk about a mathematical way to write specifications. So today's lecture is on temporal logic. Okay, so temporal logic is a form of is a branch of the area of mathematical logic. Okay, so it's we've looked at propositional logic earlier, and temporal logic is a way to write properties of a system over time. So you have just like you have Boolean operators and, or, not, etc. In temporal logic, you have operators that express properties over time, over a timeline. So we'll talk about this in the rest of the lecture. But the idea is that if you want to really reason about the behavior of a finite state machine or a hybrid system, for example, we saw earlier in the course that the behavior is really a sequence, an infinite sequence of inputs and outputs that are produced by a system, right? So an infinite input-output sequence. And if you want to represent a property of this sequence, you can do so in temporal logic. We're going to focus mainly on what's called propositional temporal logic, but there are other flavors of temporal logic that can be used to reason about timing properties, for example. And the idea of using temporal logic in general, just to reason about properties, has been around for a while. It actually originated in philosophy. So folks in the philosophy department have been using variants of temporal logic for a long time to talk about various problems in their area. But the idea of using temporal logic in computer science, in electrical engineering, came from Amir Pnueli, who won the Turing Award for that. Okay, so I want to give you an example of the kinds of real specifications that are written in practice. So here's a small snippet of the specification document of what's called the SpaceWire protocol. So SpaceWire is a European Space Agency standard for communication on board their spacecraft, and they proposed it, I think, around 10 years ago. And now it's used quite a lot, not just by the ESA, but I hear also by NASA and the Japanese agency. So think of SpaceWire as essentially a standard like TCP/IP, right? It describes how communication occurs on board the spacecraft between different computers, different sensor actuator arrays, and through routers. So you effectively have a network on board a spacecraft where different subsystems are connected through routers. Okay, so this part of the document talks about the transmission layer, which is sort of like the TCP part of SpaceWire. Okay, so in particular, this is talking about what happens if there is a reset. Okay, and the system goes into this state called error reset. Okay, so let's just read this. So this statement says, the error reset state shall be entered after a system reset, after link operation is terminated for any reason, or if there's an error during link initialization. All right, so this, it seems okay, reasonable. You think you understand what's going on, but let's look at this first part. The error reset state shall be entered after a system reset. Okay, so presumably system reset, there are implementations of SpaceWire that are purely hardware. So system reset might be, somebody presses a button and there's a signal, a Boolean signal, let's say the reset signal, which goes from 0 to 1. Okay, so let's say that's system reset. Okay, that seems precise enough, but what about this word after, right? So how long can you wait before you enter the error reset state after the reset button is pressed? Okay, I mean, this could actually have implications for cyber-physical systems, for embedded systems, because the amount of time that elapses, there's some physical process going on, and if your SpaceWire system has to be reset in time before something bad happens, it better be done quickly, right? So there's an ambiguity in this specification already in English, right? So should it be immediately entered after, let's say, a single cycle? If this is a synchronous system and you have a clock, is it after 1 clock tick? Is it after 2 clock ticks? This English specification doesn't say that. Okay. Likewise, the same thing happens here, right? In the error reset state, the transmitter and the receiver shall all be reset. So presumably there are reset states of the transmitter and receiver modules, and it's not clear if once you enter the error reset state, the control state machine enters the error reset state, whether the transmitter and receiver should be reset immediately or not. This particular specification is a little bit more precise, right? It says, it actually gives a delay. So it says when the reset signal is deasserted, then you leave the error reset state unconditionally after a delay of 6.4 microseconds. This is the European way of writing a decimal point. Okay, so the state is left after 6.4 microseconds, and then the state machine shall move to the error wait state. Okay, this is pretty good, right? So property 3 is actually telling you that when the reset signal is deasserted, you go from error reset state to error wait state, and you enter error wait state after 6.4 microseconds, right? And there is no additional condition, right? So there's the only condition is the reset signal has to be deasserted. There's nothing else. Okay, so so this is actually what you have in this document. These are this is actually it's a quarter of the page of the document, and the document runs into hundreds of pages. Okay, so how can anyone, after they build a system, look at this English and figure out if the system is doing what it's supposed to do, right? It's incredibly hard. So temporal logic is actually a way in which you can write down mathematical descriptions of all of these statements. Okay, and then it's unambiguous whether or not the system satisfies the property. Either it does or it doesn't. And the only arguments we'd have is does the English language match the temporal logic? And that's a specification issue. The human has to figure out if he or she has written down the right temporal logic. Okay, here's another example from the lecture on threads that you had a couple of weeks ago. So this is a toy example where you have two threads, 1 and 2, and there is a critical section in both threads. So C1 in thread 1 and C2 in thread 2. And the goal is you don't want both threads to be simultaneously in the critical section, right? So it's an error for the program to have thread 1 in C1 and thread 2 in C2 simultaneously. Okay, so I think when you went over this, Edward might have computed the set of reachable states, the set of interleavings of the system, right? But here we're not so interested in computing the composition of these two machines. What we're interested in is in the properties it must satisfy. So here's the first property that I just told you, right? The program should never be in state C1, C2. But you also have another property of progress that each thread should eventually reach the final statement. So thread 1 must reach D1 and thread 2 must reach D2. Okay? So these are two more properties which you want this two-threaded program to satisfy, and you can write both of those also in temporal logic. Okay. Here's yet another example. Let's say you're in your projects, in fact, many of you might be doing things like this. Essentially, you have path panning problems. So here, think of a robot which starts in a corner of a rectangular room, and let's say you've gridded up the room, right? So each of these squares is sufficiently small that it gives you a good idea of the location of the robot. And the goal is to get from the blue square to the red square. Okay, but there's obstacles. So let's say phi, which is, think of it as phi is the destination of the robot. So you can write down phi as a Boolean condition. So let's see, I might have to refresh this. Okay, so phi is, if you have xy coordinates, then here, I don't know, this is 4, 8, 12, 14, and this is, let's say, 3. So x is equal to 14, and y is equal to 3, right? So you can write down the property phi as the xy coordinates are equal to the coordinates of the location, which is the goal square, the goal state, right? And then your specification is that the robot must eventually reach x equals 14 and y equals 3. Okay, and so this is another English property, right? The robot eventually reaches phi, but we'll see that we can even write this in temporal logic. You can even write things like suppose there are n destinations. So think of a delivery bot that has, picks up papers from the office in 253 Corey, and then goes around the Corey, putting mail in the individual professor offices, right? So that would be something like this, right? You have a robot which starts out in the office, picks up mail, and then it goes to the n destinations corresponding to all the offices, and it puts the mail in all of those, right? So how would you specify a high-level goal for a robot like this? You can do that again in temporal logic. All right. So these are 3 motivating examples. Now what I'm going to do is go ahead and describe to you what temporal logic is, and we'll see a few more examples. But at the end, I would like you all to come back after the lecture is over, come back to these 3 examples and try to write down these properties in temporal logic. Okay, that's a good exercise to test if you've understood the material. Okay, so before we get to temporal logic, we'll start with something very basic, which is propositional logic. I think some of you would have seen this before. I think we talked about it briefly in the class, but you might have already seen this in a class like AI, for example. But even if you haven't seen this material, no matter, it's there in the book, and I'll go over it very quickly on this slide. So in propositional logic, you have what are called Boolean propositions, atomic formulas, which are Boolean statements about inputs, outputs, and states of a state machine. So for example, if you have an input signal x, then if I simply write down x, and x is a pure signal, then what I mean is the Boolean statement x is present, right? So if this formula, if I say this formula is true, it means x is present, and if this formula is false, it means that x is not present. Okay? So this is an atomic proposition for a pure signal. If your signal is not pure, but it, let's say, is integer valued, then I can have an atomic formula of this form, x equals 1, which says that x is present and the value it takes is 1. Okay? And if we write down something like simply write down a state, name of a state S, the Boolean property we mean by this is that the state machine is currently in state S. Okay, so those are 3 examples of atomic formulas. These are just statements about inputs, outputs, or states of a state machine. Okay, and these are atomic formulas are essentially the Boolean value propositions, and the form of the atomic formula depends on the type of the signal that you are reasoning about. Okay, so now if you write down these atomic formulas, you can combine them using the standard operators. Okay, so let's say we had 2 atomic propositions, P1 and P2. We can combine them with an AND. Okay, so this symbol is one way to write AND, and there are other ways. If you're used to C programs, you might be writing double ampersand or something like that. But essentially, these are all symbols that mean the Boolean operator AND. Okay, so we write P1 and P2 is true if both of these atomic propositions are true. This is OR, right? So P1 or P2 is true. That's logical implication. So it means that if P1 is true, then P2 must be true, and this is not, right? So this means that P1 is false. So I think we might have seen this earlier in the class when talking about guards, right? So you're not altogether unfamiliar with this. Okay, so one more point is that although I started talking about atomic propositions and as these operators as ways to combine atomic propositions, you can of course use these operators to combine other formulas. So for example, P1 can be a subformula itself. It can be x and y, right? And so you can build up nested and or expressions from all of these. Okay. Okay, let's review one more concept, which is the notion of an execution trace. So an execution trace of the system is a sequence, okay, Q0, Q1, Q2, Q3, etc., where each Qj is a triple of input, state, and output. Okay, so the way to think about an execution trace is, let's say you have a finite state machine and it's running, right? It gets inputs, it has a certain state, and it produces outputs. Let's say you're just observing what's happening in the state machine, right? So it gets input x0, it's in state s0 to start with, and then it produces output y0. So that's the first observation you make. Then in the next step, it gets input x1, it's in state S1, which may be different from S0, and then it goes to, it generates output y1. That's the next observation. So think about a trace as a sequence of observations that you make. You're just looking down at the state machine and seeing what's the input, what's the state, what's the output, and you're observing that at every step. Okay? So that's what a trace is. You can also write a trace this way. This is often more convenient to visualize. So this is saying that the machine starts in state S0, and then if it gets input x0, it generates output y0 and goes to state S1. Okay? And then this is just, this thing that we have down at the bottom of the slide is the same sequence as we have up here, but it's written in a more convenient way. Okay? So that was a quick recap of two things, propositional logic and the notion of a trace. Are there any questions about this? Okay. All right, so now let's talk about a temporal logic. So the simplest form of temporal logic formula is in fact a propositional logic formula. Okay? A propositional logic formula is simply something like x equals 1. Now if x is an input, you're saying something about the current input. You're saying the current input is equal to 1. Okay? So a propositional logic statement is a statement about the current state of your machine. Okay? So like something like the system is currently in error reset state. Okay, that would be a propositional logic formula. Okay? So using the notation that we had earlier, right? So if I wanted to write the system is in error reset state, I can simply write the name of the state. Right? That's it. So I just say the system is in error reset state. And let's say if I wanted to say, okay, the control part of the space wire module is in error reset state, and the state of the transmitter is also in the reset state. So let's say you make up a name for the name of the transmitter state, let's say TX reset, and you can construct a formula which says that at the current moment, the control state machine is in error reset and the transmitter is in its own reset. Okay. So typically, by the way, the names that you use in temporal logic formulas will be variables in your program or signals in your model, right? So they'll be directly talking about the design that you constructed. All right, so we say the propositional logic formula holds for a trace, for a sequence, if and only if it holds for the initial state. Okay. Now this is a very degenerate temporal logic formula. A propositional logic formula, excuse me, is talking only about a single state. A trace is actually a sequence of states, right? An infinite sequence of states. So when we say a propositional logic formula holds for a trace, we have to nail down one particular state that we're talking about here. And the convention is you're talking about the initial state. Okay? So we say a propositional logic formula holds for a trace if it holds in the initial state. But of course you can start your trace at any point. So let's say if you wanted to say that the formula holds in this state Q2, you can take the suffix of this trace starting at Q2, right? And that's also going to be a trace of the machine. It's not starting in the initial state, but it's starting in the second state. But it's also a valid execution of this machine which starts at Q2. Okay, so so if you take a trace starting at Q2, you can say the formula holds for that trace if it holds in state Q2. All right. All right. Now here's the one slide summary of temporal logic. Right. So this particular version of temporal logic that we're using is called linear temporal logic, or LTL. The word linear comes from the fact that you're talking about a sequence of states. Okay, and there are other versions of temporal logic that talk about non-deterministic systems where the behavior is not a sequence but it's a tree, right? So we saw that earlier, and so but for now we can ignore that part and say, okay, we're talking only about a single sequence, a single execution trace, and the particular the formalism we're using is temporal logic. So the word temporal comes from the fact that we're using these operators. So these are operators very similar to the role they play is similar to and, or, and not. Okay, so let's just go through the informal meaning, and then I'll spend one slide talking about each one of these. So we've already seen propositional formulas. So if you have a propositional formula P, the meaning, when you say P holds for this trace, it means that P holds in the initial state Q0. Okay. Now, this is perhaps one of the most useful temporal logic formulas. Okay, the way you read it is globally phi. So G stands for the English word globally, and it means that phi holds for every suffix of the trace. So phi is some formula. Let's say phi is x equal to 1. Okay, so when I say globally x equal to 1, it means x equal to 1 for this trace, which means it holds in Q0, and x equal to 1 for this suffix, which means it holds in Q1, etc. Okay, so that's the first kind of LTL formula. The second is future phi, okay, which means that phi holds for some suffix. It holds sometime in the future. Okay, so for some suffix starting at some future state of this trace. X stands for next state. So we say x of phi if it holds for the suffix starting at Q1, and U stands for until. So this says that property phi holds until phi 2 becomes true. Okay, so so let's go and look at each one of these, and then we'll do a couple of examples. Okay, so so this is just talking about the English word we use for this. So you'll often see in other books or the literature, they might use the word finally or future or eventually for f. All right, so let's talk about the first LTL operator, which is G. Okay, so so formally we say that G of P, where P is some proposition for this slide, holds for a trace if and only if it holds for every suffix. So it holds for the trivial suffix, it holds for the suffix starting at Q1, it holds for this suffix, it holds for Q3, etc., and so on ad infinitum. So we so let's just see what it means here. Actually, there's something slightly ambiguous about this slide. So let me clear this here. So we say the LTL formula GP holds for a trace if and only if P holds for every suffix of the trace. So that word should be P. And so if P holds for this trace, it means it holds in state Q0, the initial state of that trace. If P holds for the second trace, it means that it holds in Q1, right? If P holds for this trace, it holds in Q2, and likewise it holds in Q3, right? So from the definition of GP, another way of thinking about the definition of GP is the property P holds for every state in that trace. So it holds in Q0, it holds in Q1, it holds in Q2, it basically holds in Qi for all I. Okay, this kind of property is also something called an invariant. So it's often used more colloquially. You say, oh, this property is an invariant of the system. What you're saying is, no matter what state your system is in, this property always holds. Okay, so it's of this form. It's a property of the form globally P. All right, so let's talk about the second operator, which is future. So we say that future P holds for a trace if and only if P holds for some suffix of the trace. Okay, the key difference between this is the qualifier. So here it holds for every suffix, and here it holds for some suffix. So it's sort of like for all and there exists. Right? We use those in mathematics, and globally is like a for all operator, and future is like a there exists operator. Okay, so so here what it means is that there exists some suffix. Let's say it's this one starting at Q2. Okay, for which P holds, which means P holds in Q2, right? And so what it means here for this trace is there exists some I where such that Qi satisfies P, right? So there has to be one state in this trace that satisfies the property. Okay, not in contrast with the previous type, there only has to be one state, and it could be any state, right? There's no qualifier on that. Okay, so of course those are basic operators. So what makes propositional logic powerful is you can combine these operators, you can build up bigger expressions, right? And the same thing holds here in temporal logic. You can combine operators together. So here's a very common pattern that's used. So what this is saying is globally, if x is true, then sometime in the future y will become true. Okay, so this sort of thing happens a lot in protocols. So in TCP or IP, you often have things like one node sends another node a message, like to set up a connection, right? So it's called a SYN message. Since node 1 sends a message to node 2, node 2 then sends an acknowledge, right, to acknowledge that it's received the packet. So this is that a pattern that is suitable for talking about such handshaking protocols. So globally, if I initiate a connection, then sometime in the future I get an ACK. Okay. So all network protocols pretty much have such a handshaking, and a correctness condition can be expressed using this pattern. Okay. So let's reason about this particular pattern on the trace. Okay. So the LTL formula, globally x implies future y, holds for this trace if this formula inside. Okay. So here the it corresponds to x implies future y. So so this entire formula holds for this trace if the internal formula x implies future y holds for every suffix. Okay. So what it means here is that if you have let's say your trace is Q0, Q1, Q2, Q3, etc. And x is true here in Q0. And what that means is sometime in the future, okay, anywhere here y must be true. Okay, it doesn't specify the exact step at which y must be true. So for example, y can be true in Q3, right? And if x is true in Q0 and y is true in Q3, then globally x implies future y is true for this trace. Okay. On the other hand, if x is not true in Q0 but it's true in Q2, even then if y is true in Q3, it's fine, right? It doesn't make a difference. On the other hand, if x is true after y became true, and throughout here in the suffix y is not true, right? So in the rest of this trace y is false. So x became true here, but y never became true after that. Then the property is false. Okay, then globally x implies future y is not satisfied. Okay, so so in this case, for example, if x holds in x1 in Q1, and then y should hold in some subsequent state. Okay, so now let's think about this in the context of an actual state machine. Okay, so let's say you have the state machine down there. It has an input x, which is a pure signal, and output y, which is also a pure signal. And the property you want to reason about is globally x implies future y. Okay, so when I say, does this property hold for this state machine, what I'm saying is, does the property hold for every trace that the state machine can produce? Okay, so in this case, the state machine, it's a simple state machine, right? If you're in state A, there's only one transition you can take. If you're in state B, there's only one outgoing transition. So there's only one trace, right? So tell me, what do you think? Does this property hold or not? It does? Okay, why? Okay, right. So so here, when the machine starts in A, right, the only time you have a trace is when you take steps, when you make transitions, right? So when you make a transition out of A, the only way you can do that is if you get an X, right? So that the moment you make a transition out of A, this part becomes true. Okay, and now you have to have Y become true sometime in the future, but the only possible step out of B is one in which Y is output, right? And so if you ever took a step after this first transition, you will output Y. Okay, so any trace this machine exhibits has got to be of the form x followed by y in some future state. Yeah. 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 So let's think about that. So what happens if you start the trace at B? Okay. So so here's let's say I start the trace over here at B. My trace is going to be let's say B, and let's say X happens again, and I output Y, right? That's this cycle, right? So that's an easy case. There X and Y automatically are true. So let's say X is not true here, and you make this transition anyway, correct? From B to A. Now this is the first element in your trace, and Y is true, but there wasn't any preceding X, so it's okay. Now you've reached state A, and the only transition out of A is going to be one where you got an X. Oh, you can't see the sketch. I'm sorry. Yeah. So the first element is going to be something like you start in state B, right? You let's say you don't get an X, but then the transition out of B was labeled true, so you make a transition anyway. You output Y, right? You end up in state A. Now the only way you make a step out of state A is if you get an X, right? And then there is no output associated with that, right? And so so you'd end up in state B at that point, and then the next time you make a transition out of state B, let's say again you don't get an X, right? You will ultimately output a Y, right? And so here in this trace, even though originally you didn't get an X, at some future point, just because of the way the state machine is constructed, the only transition that you can make from an A will have to be on an X. So this X has to be followed by a Y in the future, and in fact it is. Dima. Yeah.
We have X and we are outputting Y, but in the future, if we stay in the initial state, we're not going to.
Okay, so the question is, what happens if you actually got an X input when you were in state B and you output a Y? Okay, in temporal logic, this itself would satisfy X implies future Y, because when you talk about future Y, the time point starts right away. Okay. Now if you wanted to specify it has to be in the future but at least one cycle forward, you need some way to count steps, and we haven't yet seen that operator, right? That's the X operator, the next state operator. So once we have the next state operator, we can write stricter properties which will require Y to be spaced a little bit away from X. There were a couple of hands up. Same question? Okay. All right, so let's see another example. Okay, so here, same formula, but a slightly different system. So note here, we have a non-deterministic system. So in state B, you can either loop back here, or you can go back to state A and output a Y. So now, does globally X implies future Y hold for all traces that the state machine can produce? No? Yeah, exactly. So technically, all you have to do to show that this state machine doesn't satisfy the property is to find one trace which the property does not satisfy. So in this case, we can produce the trace in which the machine stays in location B, right? So it starts off in A, it got input X, it's in A, and it didn't produce any output, and then it goes to state B. And now let's say it actually gets an X. So in state B it loops. So let's say it gets an X, but this is the transition that it takes, right? And so it's not going to produce any output, and that will just continue, right? So it can stay in B forever and not produce any output. And so this X doesn't have a matching Y. this x doesn't have a matching y, this x doesn't have a matching y, etc. Right? So this trace does not satisfy that property. Okay, so so now let's talk about the third operator, all right, which is the next state operator. This is going to give us some more additional power in terms of actually counting steps and expressing a different class of properties than we were able to do with the previous two operators. So we'll say that x of p holds for a trace if p holds in the suffix starting at the next state. Okay, so that's suffix q1, q2, q3, etc. So here, for example, we say that x of p holds for this trace if p holds in q1. So we'll see examples of x of p coming up. I want to make one more point here. So just like we could combine operators in the previous two that we saw, we can combine g and f. You can actually combine x operators together to count more than one step. So x allows you to count one step, but you can combine them. You can write many x's together to count any number of steps. So for example, a common way people write properties is to say something like if x must hold in 5 cycles, if p must hold in 5 cycles, sorry, you would write something like this. So you write x raised to 5p, which means 5 steps from now p must hold. Okay. All right, so the fourth operator we have here in temporal logic is called until. The until operator is a binary operator, unlike the first three we saw. So you have two arguments which you write on either side, so p1 and p2. Both of those, let's assume they're propositions for now, but they can be arbitrary formulas. They can themselves be temporal logic formulas. So we say p1 until p2 holds for this trace if and only if two things are true. So the first is that p2 must hold for some suffix of the trace. Okay, so p2 must hold either for this suffix or for this suffix or for this suffix. It should hold for some suffix. And after you fix this suffix, p1 must hold for all previous suffixes. Okay, so let's see what that means. P2 must hold for some suffix. So let's say it holds for this one starting at q3. And for all previous suffixes, p1 must hold, which means if p1 holds for this sequence, it means it holds in q0. If p1 holds for this sequence, it holds in q1. If p1 holds in this sequence, it holds in q2, right? So what we are saying really by this until operator is that for this trace, p2 should hold at some point, that's the pink state, and for all previous states, p1 must be true. Okay, this is also a common way of doing handshaking. So especially in hardware, right? People who design buses have designed protocols in the buses where there is, let's say, a particular core raises a request to access memory, right? And it keeps the request high until it gets a grant. Okay, and that's a typical pattern that you see in the until case, where some signal must be high, p1 must be high, it should be 1 until you get your request is granted. Okay, so this sort of pattern also appears a lot in protocols. Okay, so now we have seen 4 operators. Yeah. Yeah, that's a good. Okay, so all right. So let me repeat the question. So the question is, does this operator say anything explicitly about what happens to p1 after p2 becomes true, right? So for example, at this state q3, in fact, this operator says nothing about what should happen to p1. p1 could be true or p1 could be false, right? Then I think the second part of the question was, what does it say about q4 onwards? And this property doesn't say anything about that, right? So as soon as the property p2 becomes true, you don't care about the rest of the trace. Yeah. Okay, so we've looked at 4 4 operators, and let's just look at some formulas that involve 3 of them. So globally P means that P holds in all states in a trace. Future P means that P holds eventually in some state, and X of P means that P holds in the next state. Okay. So here are a few more patterns. We have seen this one already. Okay. So but let's think about these two. So this one is globally future P. Okay. So can somebody tell me what this means? So if a trace satisfies GFP, what's the pattern of P's that you see in that trace? I'm sorry? Yeah?
There has to be a P at the very end of the trace, right?
Okay, but this is an infinite trace.
So
They have to be continuously, right? Okay, good. So what it means is there have to be infinitely many states that satisfy P. Okay? Pictorially, what it means is that you have this, you have an infinite sequence, Q1, Q2, Q3, etc., right? And if P holds here, then it means sometime in the future there must be another state satisfying P. So let's say it's Q2, that's the second state satisfying P. And after you see this, at some time in the future there should be another state satisfying P. Okay, let's say it's somewhere out there, right? And then from this P, looking forward, there must be another state that satisfies P, and so forth. Okay, so what that means is there's this infinite sequence of P's, right? It happened in Q0, Q2, in some sequence of I's. Each of those should satisfy the property P. Okay, and that should happen ad infinitum. This kind of property is called a Leibniz property, right? So let's say you have one of these Mars rovers, right? You want to be able to reason about the fact that you can from any point you can always reset the rover so that you come back to a known state, right? And technically these kinds of systems are they're designed, let's say they were all designed to operate for a few months, but now they've been operating for several years, right? So you can't really predict for autonomous embedded systems how long you may need to maintain it. So that's where it becomes useful to reason about properties that hold infinitely, right? And so this is one such example of a property. Okay, let's look at the other one. So this is just the case, the dual in some sense, where you've just exchanged G and F, right? So FGP. Okay, good. So eventually you get to a state, and from that state onwards, every state satisfies P. Okay, so this is a steady state property, right? At some point, the system settles into the state from which every other state satisfies P, right? So here again, you have your sequence Q0, Q1, Q2, etc. And then let's say at some point in the future, let's say at state Q2, you have P, and then every state thereafter satisfies P. Okay. So these sort of steady state properties are also useful in systems because you often have like a reset or a reboot sequence. Okay, and during the reboot, the system is not stable. You know, certain variables may not take the correct values. But once the system is booted up, from that point onwards, you may expect that certain properties should always be true. Okay, and this is the kind of pattern that you would use to write down a property like that. Okay, okay. So I'll let you think about this one offline. It's not so different from the one we saw earlier. So, and those are the English language descriptions. Okay, so let's do a couple of examples. So here's the first one. So these are all examples of going from English to temporal logic. Okay, so this says whenever the iRobot is at the ramp edge or the edge of the ramp, which is the cliff, eventually it moves 5 centimeters away from the cliff. Okay, so now we're talking about propositional logic, and just to make the task easier, we'll choose our propositions in a nice way. So we'll make it a little abstract. So P is the proposition that the robot is at the cliff, and Q is the proposition that the robot is 5 centimeters away. Okay? So how would you write this in temporal logic? Yeah? P implies FQ. Okay. So P is the robot is at the cliff, and so when it's at the cliff, sometime in the future it moves 5 centimeters away. Okay, that's almost correct, right? But it's actually the challenge is really you have to interpret the English in an appropriate way, right? So this is a mathematical statement. So let's just see what it means. It says that if P is true in the current state in Q0, then at some point in the future Q is true, right? So you need to put something like that around it, because what the designer presumably meant by this is at all time points when the robot is moving around, if it's at the edge of the cliff, then it has to move 5 centimeters away in the future. Okay. Okay, let's see this one. Whenever the distance between cars is less than 2 meters, cruise control is deactivated. Yeah, Oren? G of P implies.
It doesn't say eventually, it doesn't say immediately, so.
Right. Right. So this is exactly. So this is it doesn't use this word eventually, right? So the one interpretation of it is, again, whenever means globally, this property is true, P is true, cruise control is deactivated. So in this case, I've defined Q to be cruise control is active. So probably you want something like that, right? So globally, P implies not Q. Okay. This actually, you have to think about this and see if it makes sense. Do you really want F here, or do you want X here? Or, but if you think about it, this property seems reasonable, because what it's saying really is when the two cars are too close, then it better be that the car is not in cruise control, right? So it's talking about really the current state of the vehicle, and so if you look at this formula inside, this is a purely propositional logic formula which talks only about a single state. Okay, so I think that would be a valid interpretation. Yeah.
Could you explain the implication of the globally on that?
The implication of the globally?
Yeah.
Yeah. So if I didn't write the globally, right? If I just wrote this, then this would say that it's a purely propositional logic formula. It says that P implies not Q must be true for any trace. So if your trace was Q0, Q1, etc., what this would say is that in the initial state, if the cars were less than 2 meters apart, then cruise control must be deactivated. But it doesn't say anything about Q1, Q2, Q3, etc. And so what you really want is for it to hold always, right? Okay, so this is actually, you can already see that going from English statements to temporal logic is a little tricky, because it depends on interpretation, right? You have to figure out whether this statement really meant globally, and whether the person who wrote this meant to put in eventually or not, stuff like that. And you can't really get away from it if you start with English. But if you start with temporal logic, then you start with something that's mathematically precise at the beginning, right? Okay. All right, so what we've done so far is we've seen 4 operators, globally, future, next state, and until. Okay, and a natural question is there some redundancy in this set, right? So for example, we know that if I have and, or, and not, then I can drop one of and or, right, and represent the other using De Morgan's laws. So for the same question here, Is it possible to express the property globally P purely in terms of future, the proposition P, and any number of Boolean operators, any number of and or not symbols that you want? Yes, okay. How would you do that?
Not future, not
Okay, so let me use the so you can write globally P as not future, not P. Is that right? Okay. So globally P is equivalent to not future, not P. Okay, so that's correct. So let's reason through this. So if future not P is true, right? So if in a trace future not P is true, it means there is some state where P becomes false, right? And that means globally P is false, right? Because globally P requires P to be true throughout. So if there's some state where P becomes false, it means the left hand side is false. Okay, and so if you negate that, if you get rid of that condition, so it's never the case that there is a future state where not P is true. It's the same thing as saying that P is always true. Okay, so I'll say that one more time. If it's never the case that there's a future state where P is false, where not P is true, then it means that P is true always. Okay, which means P is true globally. All right. So, so the answer is yes, you can express globally P in terms of all of those. You can of course express future also in terms of globally, right? And so, so you can say that future P is equivalent to, it's not the case that globally not P, right? So if P is not false throughout, it means that it is true sometime. So future of P is true. Okay, this is a slightly trickier one. Can you express F in terms of until? And again, you can use any Boolean operators you want. So the question here is, can I write F of P using some expression involving until P and any of these operators, any number of Boolean operators? Yep.
I forget which order the
Yeah, so let me, so you have, for the until operator, it's something like P1 until P2, right? Which means that P2 must be true eventually in some state, and P1 must be true everywhere until that point. You can say true until P, okay, so so what would that mean? So it means that P is true here, and then true. So true is true everywhere, which is it's a trivial statement, right? So the formula true is definitely going to be true in every state, okay? And so so that's exactly right. That will work because this certainly holds, and this is just make the requirement that P must be true in the future, okay? So the way you would write it is true until P. Okay. So F can be expressed in terms of until, G can be expressed in terms of F. Therefore, both F and G can be expressed in terms of until and the Boolean operators. Okay. Now, there's of course another question whether you can express X in terms of G, F, and U. And the answer here is it's a little tricky. We can't reason about it as easily as we did for these. But the answer is no. You cannot express X in terms of G, F, and U. And the intuition is fundamentally X is doing counting, right? So you can express plus 1, addition by 1 with X. And none of these symbols involve any kind of counting, right? And so so this actually, the proof for this actually goes back to results in first order logic of the fact that you can't express plus 1 using exists and for alls. Okay, but so you don't need to know how to reason about this proof, but just be aware of the fact that you cannot express X in terms of these operators. Okay, so far we've talked about ways to write down specifications precisely using temporal logic. Now, one thing to note here is that humans have to write temporal logic properties, right? And people have been using temporal logic in industry for 15 plus years. Okay, so companies like Intel and IBM and many embedded systems companies routinely have their engineers write what is effectively temporal logic. There's an IEEE standard language which is really a temporal logic, but it's made pretty so that people who are not trained in mathematical logic can write these easily. And what they've found is that people tend to write, in spite of all the aids, the pretty syntax and so forth, they tend to write properties which sometimes are mutually inconsistent, right? And so it can be really hard to write properties. So there's always this human judgment to figure out what is a suitable property, what constitutes correctness, and getting the specification right is often as hard as getting the design right. Okay. But it's something that you have to do, because unless you get the specification right, you can never be sure that you're building the right thing. Okay, and so more recently there have been more tools that will automatically check if your specification is inconsistent, so you know immediately that something's wrong, and so there are tools built into the IDEs that people use. But this is something to be very careful about when you write temporal logic. Think about it carefully and reason about it using state sequences to make sure you've really got the property you want. Okay, so as an exercise for you, when you go back home, you should try to write the space-wise specifications in temporal logic. Okay, so these are the 4 properties I showed you in an earlier slide, and you can make up your own variable names, your own signal names, and write these properties. But I think this is something that you should definitely do, because it'll tell you what happens in the real world when people try to write precise properties, and B, it'll familiarize you with the notation. Okay, and do the same thing for the other examples I showed you, which is the robot and the thread example. Yep, Dima. Yeah. Yeah, so, okay. So let's go to the definition of P1 until P2. So the definition is, so P1 until P2 holds if and only if P2 holds in the future and P1 holds in every state until P2 holds, right? So there's 2 components of the definition. P2 should hold sometime in the future, and then for all states before that, P1 must be true. Okay, now what's the definition of future P? So future P is just saying that P holds in the future, which is the same as the first part of the until definition, correct? So in some sense you can already see that this is a weaker requirement than until, because until requires the future part plus something more, correct? So one pattern match you can do is, if you replaced P2 with P, then you would get the requirement of future P, right, for free, but then you would have this additional part. Now what we want is to pick a choice for P1 so that this becomes trivially satisfied, right? And what would be that choice that it holds in every state? Well, true, right? So the trivial formula will hold in every state, and so if you set P1 to true, then this expression, this definition collapses to that definition, right? And then you get true until P is equivalent to future P. Okay, yeah? Can you say not P until P? Okay, so the alternative proposal is can we say something like this? Not P is true until P. Okay, so the difference would be that you're requiring that not P holds in every state until P holds. Okay, which so remember we're reasoning about from the initial state onwards. So what we're saying is P holds at some point. So P holds at some point here, and if this is the first occurrence of P, then we know that not P holds throughout, right? Now, so that, suppose what happens if P holds at some future point? So there are two P's. I guess that trace still satisfies Fp because of this, and it still satisfies not P until P because of the prefix. Yep, I think this also will work, right? So I guess the way to reason about whether or not two temporal logic formulas are the same is you look at all traces satisfying future P, and you have to prove that they satisfy this. You look at all traces satisfying this, and you have to prove that it satisfies future P. Okay, it has to go both ways. So if I look at any trace satisfying not P until P, it certainly satisfies future P because that's the first part, the first component of the until definition. Okay, so any trace satisfying this will satisfy future P. So what we need to reason about is going the other way. Any trace satisfying future P should satisfy not P until P. Okay, so the way you do that is consider an arbitrary trace which satisfies future P. Okay, so that means that there's at least one P. One state satisfying P. Pick the earliest such state. So that's this one. Okay. For that earliest state, every preceding state satisfies not P, right? And therefore, it satisfies not P until P. Okay. Now, let me make sure that works. So what happens if this was the original state? So suppose this was Q0, the earliest state satisfying P was in fact the initial state. It certainly satisfies future P. Does it satisfy not P until P? Yeah, that still works because if you take P to be the initial state and there is no state before it, so it satisfies not P until P. Okay, so in fact these two are equivalent. No, okay, so the proposal is can you say false until P instead of true until P, and the answer is no because there are sequences that satisfy future P but not false until P. So let's so the question is if I wrote false until P, is that equivalent to future of P? And so what I'll do is exhibit one trace which satisfies this but not that. Okay, so let's say that's the trace when in the second state you have P true and not P is true before that, right? All right. So this is the trace which satisfies future P, but it doesn't satisfy false until P because no state satisfies false, right? I mean, so every state is some evaluation of variables, right? So let's say the only variable I have in my system, the only signal is P, either it's present or it's absent. So either P is true or not P is true in any state. I mean, false being true would be like it's a condition which excludes either P being present or P being absent, right? And so that's typically false is never true in any reachable state of your system. Okay, so in this case you can't say that false is satisfied in these two states, and therefore this property is not satisfied by the trace, but future P is satisfied by this trace.
You
false until P, no, false until P will be equivalent to false, because, so this part will be P holds sometime in the future. This part would be that false holds in every state until P holds, but by definition false cannot be true in any.
Would that be satisfied by a sequence which started with?
So given a sequence that satisfies, that starts with P, yeah, false until P will hold for that sequence.
So is false until P equivalent to P?
No, because it only holds for that particular trace. So when you say, the question, are two temporal logic formulas equivalent, it means are they equivalent for all traces, right? So, but not for a particular trace. What you showed me was a specific trace where P is true in the first state. Right? For that trace, or for all traces in which P is true in the first state, false until P will be equivalent to P. But not all traces necessarily have to have P true in the first state.
Another P means, not future P, but just P.
So again, P is just by itself, P is just a formula. When I say P holds for a trace, it means it holds in the first state. But there could be traces of your system where P does not hold in the first state. That's right. So we can think of an example. We had this example where we had two states, right? You had state A and state B, right? And suppose I have the formula B, which means B is true in Q0, the initial state. This formula does not hold for this system because when you start out, you're in state A, you're not in state B, correct? So this is an example of a simple temporal logic formula, just a propositional formula, which is not true for any trace that this system can exhibit. All right? These are all great questions. I think it's showing the fact that temporal logic is a little subtle. So go back and read the chapter 12, okay? And if you have any questions, we can do a few more exercises at the beginning of next class.